Thank you very much for attending this talk. My name is Daniel Carvalho. I run business for Wolfram in Brazil. I'm a computer engineer, master in electrical engineering, and my first contact with Mathematica was in version 4 in the labs, college labs, the Calculum classes a long time ago. And then I've been doing math, calculated then on PC, computing math ever since. This conversation here is a subject I've been ever interested since undergrad, that is about random numbers, how to have them and how to check them. If we have a list of numbers, integer, binary, or real numbers, I would like to know if this list is real, kind of random, and then at the same time to be able to create those data, numerical data that is random. The funny thing is, when we learn it in the beginning, what is really weird is that professors state this is hard to do. It's even hard to create random numbers or to know if a sequence of numbers, if they are really random. And the obvious source for randomness would be kind of fractals. And then let's check this out, what we can do with fractals. First of all, I have published this demonstration for some time. And here I compare the pseudo-random numbers with some mathematical constants, some real values. I break down here, for example, the digits of pi and plot here, okay? And then it seems to be really random, but we can calculate. There is a easy formula to calculate the digits of pi. And when you compare this with a pseudo-random number, visually we get notice that this is some deterministic. Pi is deterministic. Let's try to make it smaller. We can navigate, for example, highlighting the digits and the sequence, and it really seems to be random. As we have more numbers, we feel that there is more randomness. But this at the right side, the image at the right side is pseudo-random, and this other one is pi, is the sequence. And then when we measure like the mean, total, or we measure standard deviation or any statistical property of those sequences, they seem to be random. And even more strange, like the other real mathematical constants that are very deterministic, we know how to calculate the golden ratio, E, or lambda, all of them, we can notice the same behavior. We can change here our random image, and here we can compare with the real numbers, and it looks like the same thing, like they are. It seems to be random, but they are not random. Another visualization about those real constants, we break down the digits. Okay, here we break it down in 1,000 digits. When we plot in the histogram, you may notice they tend toward a uniform distribution. And then it seems the numbers, they goes to the same frequency, kind of the same frequency. And as more numbers we have, more stronger, I may say, we have an uniform distribution. Another example here. This demonstration, I'm using random numbers. I'm using the internal random seed from Wolfram Language, but the method here is the Wool 30 from cellular automata, the elementary cellular automata U30. And then those pseudo-random numbers made with cellular automata, we have this behavior, the same behavior, like they move toward uniform distribution. By we notice by the histogram, smooth histogram, or a simple pie chart, they are very close. Counting the number of digits we have, here we are talking about 100,000 digits, and they are, as more digits you put here, more they move forward to a uniform distribution. Here's a visualization about white noise. Here I'm controlling, I'm enforcing a uniform distribution for a white noise process, and we get a sample data, 2,000 digits, a sequence of 2,000 digits from white noise, and then we have a visualization. This first one is a ray plot with the digits itself, and then here is a frequency. We calculate the Fourier, the absolute value from Fourier, and then we can see a frequency version of this data. And then here we have another Fourier. Here we see the density. It's sparse, like 1.5 to 1. Around that, it's sparse, the frequency of numbers, and then around 0.5, they are more dense, using uniform distribution from a white noise. Here, it's another visualization, a log-log visualization from the Fourier. And the histogram go towards uniform distribution too, when you talk about working with white noise. Here, two other visualizations. It's a list plot from the sequence here. And then I have the list fit plot, and the distribution seems to be here like smooth. They seem to be smooth. They don't seem to be grouping somewhere. And then the fit plot here gets crazy trying to fit the data because it's noise, and so this fit line here highlighted in blue. This line is a kind of random to try to using machine learning in order to find the fit. Here I have a function to analyze with some statistical measurements, evaluating here this sequence white noise, this original list. And here we have the standard deviation, the variance in gauges to figure out how they behave. What we can do here, we can, for example, to create a manipulate and add more digits in order to check how those values evolves on time as we add more information with bigger samples, and we can figure out how they vary by the statisticals, the descriptive statisticals parameters. Continue talking about noise. We have a very nice resource function that is this colored noise. We have a couple of named noises here, colored noises, and we can explore in a manipulate, in interactive visualization. This is the brown kind of noise. We can change here the number of digits. And then here, the first image is the sequence itself. Okay, this is an image. It breaks down the sequence for us to see this in the lattice. Here is the Fourier 2D visualization. Here's again the Fourier, but we are seeing here the frequency of the numbers. And here the log-log from the Fourier again, we have a interesting perspective where those frequencies goes. And down here we have a histogram. See, look, that this is really different from a more flat distribution. It's very different from a kind of smoother distribution. We can change here the noise type. Okay, for example, the brown and the red ones, those two distributions, they are more like different. They are not well designed to create random numbers, okay? Sets of random numbers. But for example, when you go to white noise, here they really seems to look more like a random number, random set of numbers. It happens when we look at the frequency, and here we have a more smooth distribution here in the frequency, and here is a normal curve in the histogram. But we can take a look at the other, like violet distribution. They have some differences here, and then we can do it again. Look those graphics to visualize the difference from those noise pseudo numbers using this resource function colored noise. We can do it side by side. We can look at side by side here at the first image, like the violet, the purple, and the blue kind of noise. They seem to be random, and in the vision from Fourier is the same perception for a visual analysis. And then we can look now those three other graphics. We have a better visualization. Like here we have the Fourier, here we have the log, and here we have the histogram. We may notice, comparing those different kinds of noises, we may notice that the brown and red, they are the most different kind of noise. They have some frequencies that they are more intense, higher than the others. The histogram is really different from a normal distribution. They have a very particular distribution. The other kinds of noises, they are more tending to toward the normal distribution. But here, for those noises, brown and red, we have a very different histogram. I like to use the elementary cellular automata rule number 30, because they create, when we start, for example, with one cell as initial condition, and move forward to evolve the next steps, this central cell, they are random. We can create random numbers from elementary cellular automata rule. That's a simple rule explored in the New Kind of Science, if you will, from book. What I do here, I use it as a source of random numbers. Here I process like 10,000 steps, and then I get just the central cell, just the data from the central cell. And then we can look that this is the central cell. This is a central cell because it starts with 1 at the initial condition. So I can double check here if I am getting the right stuff. Again, I break it down and plot this as an image. It's a binary image. We have just 2 values. And then it looks like a random image. When we measure the amount of black cells and white cells, zeros and ones, they are very close. They are very close, like a more smooth distribution. And then we have very nice randomness test functions at the resource functions too. Here I'm trying 3 of them to measure this list of binary numbers I get from the central column from the Wool third cellular automata. And then here we have this p-value. This p-value, as higher, they are better. When we have a sequence of random numbers and this p-value gets higher, they are better than lower value for the p-values. They goes from 0 to 1. So we have some nice analysis here for those central binary numbers from the Wool 30 using those random test functions that we have available at the recursive function. We are using 3 of them here to analyze the same sequence of the 10,000 first binary numbers from the Wool 30. Here, another example doing the same kind of analysis from real numbers. I get real numbers here from Wool 30 again, behind the scenes with CD random from Wolfram Language. And then I'm using here, let me show you here, this run count randomness test. We have the p-value again, and we can change the size of the sample and then verify how the p-value evolves, how they goes, and we have more numbers. .7, it's a good p-value to validate as or to use those numbers as random numbers. Again, with using the noise sequences, created the noisy sequences, using those measurements for randomness. Here we have a pattern made by a red noise. We have here in the interface the red noise, and then when we measure it in a sequence, in just as one vector, all this data not broken as an image but as a sequence, we have here the p-value, and here we have the entropy. We calculate the entropy too. For example, let's see like the white noise, how they behave. It's taking a bit to compute. Oh, here we have it noise. The image has we have the feeling of noise in the image. Oh, now it gets a higher p-value. Let me try to have more digits. I'm waiting for the computation. Okay, let me try again. Oh, here, it's back. And then I can resize the amount of data sample, amount of digits we have. And here we can change the kind of noise to do an analysis. And then the white noise gets higher values here when you calculate the p-value for this randomness test here, the run counting. We can try to do the same thing for a bad value. This is a repetitive pattern, and so it gets a very low value for this repetitive pattern here, because it's really bad for to create random numbers. This is our test case. Our test case here. And about fractals, this is just for fun, but fractals seems to be nice to create random numbers, but that's not true. we can navigate and get really nice patterns and complex patterns on fractals. But sometimes, in some cases, we can have a lower entropy data, lower entropy images when we navigate at those fractals. Here, for example, I get an initial condition, a Mandelbrot set, initial condition. I get just the data, the matrix with the pixels with RGB values, and then I get them flat and to check what we have. And the histogram shows that this is really not good for a random number. Okay, we have some spots here that are huge, and we have other very low values here, and so this is really no good for random numbers. And then we have here the smooth histogram, and again the Fourier, the absolute value from Fourier in a list plot. And it's possible to notice we have here some sparse cases here at the top, and here we have a more stronger frequency of those numbers, or usage of those numbers, and then it is really not a good for random numbers. Calculate the p-value from two measurements here for randomness, the run count and the t-square. The value is too low. It's too low, so it's really bad idea. Try to use those guys as a source for random numbers. And here it's exactly the same thing, but here I am doing this for Julia sets. It's exactly the same steps, and we have the same result. We can try to do something. We can try to do something, but we should have to define some strong boundaries. Strong boundaries in order to choose what kind of fractal patterns we can extract random numbers, or for some specific proposed application, we can figure out how to create some boundaries and then to use them as sources for randomness. Here again, trying the randomness for randomness from cellular automata, from elementary cellular automata. And here's some hints about these random tests. We have some random tests that they work with binary numbers, just zeros and ones. And we have others that work better with real numbers from 0 to 1. And here, when we have, for example, here we have just the number 1. We get a very low value. It's very bad. This data here, this list is very bad for random numbers. Here we have using random integer from Wolfram Language, and then we have a good value here. We have the p-value for this list that came from random integer that is using rule 30, because I'm forced and I'm set here in my notebook in order to use the rule 30 as a seed, and so it works. It's a good value. When we try again, like here I am trying another list, but this is a lower entropy list. This is a identity matrix. In this identity matrix, there are lots of zeros and a couple of ones. When we run the test, we have a very low value. It's very bad for randomness, for pseudorandomness. And here, the random integer, using the random integer, we repeat. We have a random integer list from with 10 digits, 10 binary digits, and we repeat them. We repeat them 20 times. And then we have a good p-value here. But this is really no good, okay? I am repeating 20 times the same random list of binary numbers, and then when we test, they say the p-value is good. And so this is really This is really bad, right? It's not a good sequence for random numbers. And here we can navigate on those cellular automata rules and measure for the pattern of the cellular automata how they behave to create random numbers. We have here the entropy. We have a compression ratio. We compress and you measure how much the data is compressed. If the data they have repetitive patterns, we can compress a lot. If they are random, we can't compress them much. So this is a measurement to check if we have something that has a more random behavior. And the entropy is the opposite. When we have repetitive data, the entropy is low. When we have a mass, it's a mass of data, the data is kind of random, they go up to 1. And here we are using the measurement for randomness for a random sequence. The p-value again, as higher is better. When we try, for example, the rule 30 with a random initial condition, don't seems to be good. It's a low p-value. It can be compressed, and the entropy, the entropy, it's higher. Let's try this other rule, 76. Oh, here we have a 0.7 p-value. It's better. This pattern here is better for randomness. Let's see rule 110. Oh, rule 110 is very bad. It's very low value, okay? It can be compressed a lot. It's interesting. And this rule 151, it's bad. It's bad. If you get some rules like if they are, for example, they converges like a class 1, they converges to just one value, they are terrible. They are terrible. We can compress a lot. The entropy is very low, and the p-value is really, really bad. And then we can measure, and oh, this is another very repetitive pattern, inappropriate for random numbers. And then we can figure out here, measure those rules, create more numbers in order to, oh, look, this is nice, but it's very repetitive. We have basically two values by steps here. Okay, so it can be very compressed, very bad p-value. And then, just to finish, we have the same thing again, but for a totalistic cellular automata. We have here some rules for sample, and then this rule here, we have 3 colors. And then the compression ratio here is high, but the p-value is high too. Interesting. And the entropy is high, the compression rate, the compression rate is low. They are fine. Let me see the other rule here. Oh, look, we have here again a low p-value, good compression ratio, and higher entropy. Let me try this other rule here. And this other one. And then we have tools to measure patterns from cellular automata, totalistic or the elementary cellular automata. We have resources to create random values. Fractals is hard to work. You should have some strong parameters in order to have sure to don't get in low patterns or low colors data in order to extract some kind of randomness from those from fractals like Julia set or Muldebrot. But cellular automata, they are good. We have here good rules, and we can measure those rules to figure out those we can use in our projects, in our research projects. Thank you very much to attend this talk. This is our presentation for today.